Okay. So it looks like we are live. I don't know if YouTube is going to show like a slight delay. I'm gonna check, make sure that we're doing everything wrong. Okay. Looks like we are live. I'm gonna close that window real quick, because it looks like everything is recording as it should. Those of you who are following us remotely, hi, thanks for coming. We're going to talk about machine learning this evening. Don't worry, you won't have to just look at my face for an hour. I will mostly be showing my slides and then a demo of some machine learning techniques. You'll just see me at the beginning and the end. So if you just somehow wandered in here randomly, we are going to be talking about uses and misuses of machine learning. And I will go ahead and switch over to my slides. Actually, this is my first time broadcasting, so be gentle. There we go. Okay, so application window. There we go. So hopefully you can see my. It looks like you should be able to see my presentation, and we're going to start from the top. Okay, so I'll talk a little louder. So now this is the beginning of the presentation proper. So our topic for tonight is machine learning, uses and misuses. I'm Danielle Gaither. This is part of our summer series, our being TechMill, and I'll talk more about who TechMill are later in the presentation. And this is just a free series of educational events on various, mostly technical topics that are relevant to the TechMill community. So who am I? For those of you who don't know already, this picture more or less matches what you see in front of you, hopefully. I'm the president of TechMill. I'm a PhD candidate in computer science at UNT, and I have actually used machine learning to some degree in my research. So it's not like I just Googled a bunch of stuff and threw it on slide. This is from lived experience too. So what am I going to talk about? I'm going to give you a brief overview of what machine learning is, its history, the kinds of things it's used for, ways to use it, ways to misuse machine learning. I might spend more time on this section than any other because I feel like there's a lot of misinformation about machine learning. So I want to help dispel some of that misinformation. And then I will provide a demo of some sample machine learning tasks, and then give you some resources for further learning if this piques your interest and you're like, hey, I'd like to learn more about this fancy schmancy machine learning stuff. So we're going to start with the overview. So the origins of machine learning. The main idea behind machine learning is to emulate learning by example on a machine. If you think about how people acquire language, people don't, or at least how they acquire their first language. It's not in a classroom with verb tables and things like that. You just kind of pick it up from hearing people around you speak that language, and you get better at it the more you do it. And the idea is to emulate this process on a machine. And it's important to have that basic understanding because I think that is really helpful in determining what you can and can't do with machine learning. So when you understand that, regardless of the details of the algorithm, this is basically what it's trying to do, that I think helps you get a better grasp on, solving a problem that you might wish to solve with machine learning. And it grew out as in the late 60s and 70s out of more general artificial intelligence. I think the idea of general artificial intelligence, like sentient robots and that sort of thing, has more or less fallen on hard times since the 1980s, but specialized applications such as machine learning and natural language processing, which has some overlap with machine learning, we've had a lot of success with those. As soon as we don't try to expect these things to be all things to all people and have a more realistic idea of what they can do, then we can maximize those to the best of our ability. And one of the earliest applications of machine learning was checkers, then eventually moved on to more complicated games like chess, and in the last 10, 15 years, we've even moved to a very complicated Chinese game called Go. And if you think about it, checkers is a very simple game with very simple rules, and you just you feed a series of moves from a series of checkers games, and it gradually learns how to play checkers that way. So here's the question I promised to answer in the meetup, if you guys came here through the meetup page. There seems to be a lot of talk in the general popular discourse about a potential robot revolution, and I think there's a lot of fear-mongering with respect to artificial intelligence, and I think most of it is way oversold. I do not worry at all about robots becoming sentient and overtaking us. I don't worry about Skynet or Westworld or any kind of situations like that. So if you were worrying about that, let's all take a breath. We don't have to worry about that. What I do worry about, and I'll talk about it especially in the misuses section, is technology being used for ill by the people who power it. And so that is something that probably should keep you up at night. So sorry that our relaxed state was short-lived, but this, if somebody is talking about this robot revolution seriously, that's, I think, a fairly good sign that they don't actually know what they're talking about with respect to machine learning and artificial intelligence. They've just watched too much sci-fi and taken it too seriously. So some ways to use machine learning. You have used at least the benefits of it maybe today, almost certainly recently. A very simple, trivial one is those filters on things like Instagram and Snapchat that, where you can put koala ears on your face and that sort of thing. The way they get those to work is they feed in a bunch of faces, and it gradually learns to detect where the eyes are, so it knows where to put the sunglasses on the filter. That sounds like a trivial thing, but that's an example of how machine learning is frequently done. So some common applications. Think problems that humans can solve, but faster. So, obviously a human could go, if you handed a human a stack of photos and said, okay, circle the eyes on all these photos, they could do that. But once you train a machine well enough, presumably a machine could do that a whole lot faster. And that's what if you want to get the best out of machine learning, that's the way to think of it. It's not magic. It's not like you just feed a bunch of numbers into an algorithm and poof, the meaning of life pops out. That's not how machine learning works. But if you think problems that humans can solve, but doing it faster, that's where the most effective applications of machine learning tend to be. So one of the most common classes of problems that machine learning is used for is something called classification. And this is something like spam detection. So if you feed it a bunch of emails and some of them are, you tag the ones that are spam, and it gradually learns from reading all those different emails, and it's like, okay, these words tend to come up more frequently, there we go, in spam, and these words appear less frequently. There's a little more to it than that, but you learn an outline of what spam versus a legitimate email looks like. And then language detection, if you use Google Translate at all, now you don't even have to put in the source language most of the time. It will actually detect it for you because it's been fed all kinds of samples of all kinds of languages. And so it's actually pretty good at detecting it for you, even when the languages are somewhat similar. Like Spanish and Catalan, it's pretty good about telling the difference. Segmentation is another common application of machine learning. Clustering is another name for this. So say you have a bunch of customer data and you want to group similar behaviors together. In the past, this has been done mostly by demographic information like age, zip code, and that sort of thing. And that can still be useful, but there are other ways. Like if you have a Netflix account, it'll say, it'll say, based on watching these movies, we think you'll like independent dramas with a strong female lead, like this one. And so that doesn't necessarily depend on your age or your zip code, but it focuses more on behavior. It looks more at your past consumer behavior than your profile data. And so that's another example of very effective use of machine learning. So ways to misuse machine learning. This is my favorite section. So this is more about fear-mongering and misguided ideas. One of the most common ways to misuse machine learning is to treat it like it's magic. Like I said a few minutes ago, like you can just pour a bunch of data in and some result that will be meaningful and accurate will magically come out. That's not how it works. You need good data. If you don't have good data, then it's highly unlikely that machine learning is going to be a good fit for the problem you're trying to solve. Now, what is good data? Ideally, you have a lot of it, and ideally, it's not tainted in some way. That's actually a hard thing to do. It's harder than any of the algorithms or anything like that. Is actually the hardest part is actually getting good data for the problem you're trying to solve in the first place. So that's something to be mindful of. But ideally, you have lots of it. It's well structured. It's clear what all the data is. If you work with data at all, you probably won't be surprised how often that is not the case, but if you don't, you would be surprised how often you look at like a spreadsheet or a database and you're like, what do all these abbreviations mean? I have no idea. So, and then like I talked about earlier, can a human solve this problem? Chances are, if a human can't solve the problem, and I'm not talking about time. It's not necessarily can a human solve this problem quickly, but can a human solve this problem at all? Because there are certain intractable problems that a human can't solve, like which is better, chocolate or vanilla? Well, chocolate, of course, so maybe that wasn't a great example. But that's the sort of thing you wouldn't want to turn to machine learning for, because that's a personal preference thing. If it's the sort of thing that you can solve with enough time, then machine learning is a better fit, because it can. The main advantage of a machine is speed. Is that it can crunch numbers faster than any human. So if you can find a meaningful numeric way to represent your problem, then that makes it a better fit for machine learning, because machine learning can crunch numbers faster in the vast majority of cases. It's also important to remember that machine-produced results can still have flaws, because a program, an algorithm, a spreadsheet is only as good as the people putting it together. And so algorithms have the biases of the people who create them. A lot of, something I see a lot is, people assume that because something has computational origins, that it's also morally neutral. And that's not the case. There's still, behind every computational decision, if you look far enough, is a human decision. And so you can't take those out of the game, because the machine is what you're interacting with most of the time. Excuse me. Excuse me. So an example of what I'm talking about is how algorithms have the biases of the people who create them. This was detailed in the book Designed for Real Life by Eric Meyer and Sarah Wachter-Becher. I highly recommend this book. I met one of the co-authors, and her talk was amazing, and you should totally check them out. So I'm presuming most, if not all of you, are on Facebook, and you know how at the end of the calendar year, you get that year in review feature. It's like a video, compilation of some of your most popular posts throughout the previous calendar year. And the thing is that something as seemingly benign as that can have a lot of unstated assumptions with unpleasant consequences. For example, what if you haven't had such a good year? I mean, we like to think every year is a good year, but one of the co-authors of this book, when he encountered this feature, he had, of course, it has the post with the most engagement. And for him, he had lost a child that year. And so he had posted a photo, announcing that his daughter had passed away. And so, of course, there were a lot of people offering their condolences to him. But then he was greeted with that at the end of the calendar year. He's like, oh, here's your kid who passed away. And that naturally did not make him feel very good. And, we can all think of time, we've all had enough years on this planet to know that some are better than others. And there are some times when, an automatically generated video review of the previous year would not be super welcome. And so since then, they've kind of toned down the language and the decoration, because at the time they had these really festive decorations, and they were like, it was like, here's your awesome, year 2014 or 2015, whatever it was, just click the share button to share it with others. And he was not into that for completely understandable reasons. So technology is no substitute for mindfulness. When you're setting up features like this, you still have to consider, like, well, might somebody be seeing this in a bad mood? So there's, again, there's always a human decision behind every computational decision. And so I would say it is not wise to disregard those human decisions. So, of course, this is this is not machine learning per se, but Jeff Goldblum's character famously said in Jurassic Park, your scientists spent so much time, considering, asking how they could regenerate dinosaurs that they didn't bother to think whether or not they should. I'm paraphrasing here because it's been a long time since I've seen the movie, but that, I think, any new product or algorithm you design, I think you should have that in the back of your mind. Like, what is this going to be used for? How could this be misused? Who might not take this well? It's, technology is no substitute for mindfulness. So another way you can misuse machine learning is expecting it to do all your thinking for you. You still need basically the same things for any scientific experiment. So you need like a well-defined problem. So like with the spam example, as a way you could frame that in a way that's useful is, given, a set of emails for training, can I predict whether an unseen email is spam or not? That's a precise, answerable question. You could even extend it as like, okay, could I predict, 1,000 emails with 99% accuracy? Or whatever, you can get as precise, but that's the kind of mindset you have to think. It's not just, oh, I just throw the data in the numbers and something useful comes out. You need a means of measuring results, and that is going to be dependent on your particular problem. Like with a classification problem, accuracy, I think, is a reasonable measure. How many emails are classified correctly? With the segmentation thing I issued earlier, I talked about earlier, you could see how many consumers follow the recommendations you give them, and if not as many as you'd hoped follow the recommendations, then maybe you need to reevaluate how your recommendations are being done, that sort of thing. So it's machine learning is science at its heart, and it has, at its best, the same setup as any good scientific experiment. You have your materials, your hypothesis, your means of testing, and then how you evaluate the results. And as long as you stick within those parameters when you're using machine learning, then you're a lot more likely to get good results, I think. So, and then as I mentioned earlier, just because something is an algorithm does not mean it is free from bias. There's tons of examples of that. So some more examples of, so here's an example of like expecting the data to do all your thinking for you. This is from the book Smarter, Faster, Better by Charles Duhigg. He was a journalist at the New York Times. And Air France 447, some of you may remember this, it was an airplane that crashed into the Atlantic off the coast of Brazil. And when they eventually recovered the flight data recorder, they found that the crew was overwhelmed by these small pieces of data, and they didn't look at what was obviously going on around them. And if they had taken some time to survey the scene, they probably would have taken different corrective action than what they did. And more interestingly, in this book, a similar malfunction happened in a Qantas plane, but it was handled differently because the pilot in charge of that flight relied more on his experience as a pilot and kept taking everything as a whole picture. And that plane was landed safely without injury to anyone. So it's, remember, data is just a tool. It's not magic. It doesn't do things for you. It does things humans can do, just faster. So if you keep that in mind, that's very helpful. So now we get to the machine learning demo. Let's see, we're back to my face for a second. For those of you watching the live stream, I'm going to switch to an application window. Here we go. Switch to my browser. And we're going to look at an example. Okay, make sure the screen share is working. Go ahead and maximize this puppy. Okay, so this is from a website called Kaggle, and this is a great place to get your feet wet with machine learning if you want to learn some of the basics with some publicly available data sets. Kaggle is a great site for that. And so a classic introductory example for machine learning / data science is passenger data from the Titanic. Of course, well, actually, I shouldn't assume, because I actually had a colleague who's not from here ask me what the Titanic was. The Titanic, was a ship that sank on its maiden voyage in 1912, and the survival rate was not very good because they didn't put enough lifeboats for all of the passengers and crew. And of course, the 1997 film Titanic, kind of touches on this as well. But again, the whole reason we're interested in this is not because of the data set, but because of some bad human decisions that led to bad outcomes. So is this the one that I was using? Yeah, let's make sure that I'm going to make sure that the Hangout is showing this as well. Okay, good. All right, so I'm going to fork this notebook, and I'm going to actually walk you through some of the processes, not just the algorithms, but a lot of the, like data science as a career path is very hot right now. It pays well, and you can work on some interesting problems, but that doesn't mean every bit of the work you do is going to be interesting. A lot of time spent working with data is doing a lot of grunt work, like making sure that data is computer readable, making sure you have all the data you need, that sort of thing. So, okay, this is taking its sweet time to load. I apologize for that. But once this loads, this will walk us through the oh dear. Don't tell me what to do. Okay, why is it taking so long to load? So I might have to, okay, let's not do that. Let's try this one more time. I don't want to commit anything. I'm a commitment phobe. Yeah. Okay, so it doesn't seem to want to set up the interactive version. That is okay, because we can just walk through the existing one. So yeah. So unfortunately, we won't get to actually demo the code, but I'll walk you through the steps. Now, this is a good example of some common tools for that are used in machine learning. This is something that's called a Jupyter Notebook, which is a tool for Python. Python is one of the most common languages for machine learning and data science applications. And the cool thing about Jupyter Notebooks is you can mix code in with documentation like you have here. And then you can save it to a file and then send that file to anybody or post it on a server, and then they can run it interactively. You can run things, I'll scroll down a little bit. So you run this section of code, then you can look at some more documentation, then run this section of code, and so on and so on. So for the ones that have output, we've got the output below, so that I can at least walk you through that. And so with the Titanic, we have pretty thorough, especially for the time, data on the passenger list for that ship. You know, we have people's names, their ages, who they were traveling with, how much they paid for their ticket, what class their ticket was, you know, which cabin they were in, that sort of thing. And so this is just importing all the libraries you're going to be using later, so I'll skip over that. And then this is, I'm going to talk about this a little bit. Anytime you're using machine learning, you need your training set and your testing set. If you want to get fancy, you can also have a validation set, but I'm not going to get into that tonight. You need to split your data, and depending on how much you have will depend on the percentages you have, but like 80-20 or 70-30 are pretty good examples of train versus test splits. Your training data is what you feed into the algorithm to build your model, and then your test set is what you run through it to see if it classifies things correctly. So, excuse me just a second. Something you have to watch out for, and I probably should have put this in the slide, but there's something called overfitting, and that's where your model just memorizes all your training data. And the way you know it's done that is having a very low error rate for your training set, but a very high error rate for your test set. So when you, if you run into that, that almost certainly means you've overfit your model. And you don't want models that just memorize your training data. You want models that you can generalize to unseen data. That's the whole point of this approach. So this has the train and test split already. So that's what this, when you see train and test, that's what it refers to. Yes? It actually has the number. It was like 800 and something, 891. So that's how many records they have. I think there were more people than that. So, but we have 891 passenger records. So, so yeah, when we get to that, I'll talk about we'll look at some of the data that they have. And so you can actually print the column headers. And so this is, passenger ID, whether they survived or not. They have a 0 for those who didn't survive and a 1 for those who did. P class, that's whether they were first, second, or third class. Passenger name, that's sex, male or female. Age, again, fairly. Now see, this is the kind of stuff that I know what SIBSP and PARCH stand for because I've looked at this data before, but these are the kinds of things that you can run into. SIBSP is siblings and spouses. So how many siblings and spouses they had? Well, presumably just the one spouse if they had any, but for some reason they were, so like if you had your spouse and 2 siblings with you, this would be 3. That sort of thing. And then PARCH is parents and children. But these are the kinds of things that you'll encounter. You'll see these like weird abbreviations, and sometimes you have to shoot some emails or look some things up. And then the ticket is the actual ticket number. And then the fare is how much they paid for said ticket. Cabin is their cabin number. And then embarked is the port where they boarded the ship. So this is the data we have available to us. Some of this data is going to be more useful than other data, as you might expect. So another thing to think about is the types of each, what they call, each of these, by the way, is called a feature. So passenger ID is a feature, survived is a feature, and that's what all of these are called in machine learning, is features. And generally what you have is you have all the features, but the one you're trying to predict set aside, and you try to see if you can predict, in this case, whether a passenger survived or not based on all these other features. So two of the most common types of features are what are called categorical and numerical. Numerical is fairly self-explanatory, something that's represented by a number, like age or see, class could actually be either one, but I think it's easier to think of it as ordinal or categorical for reasons I'll get into in a moment. And so which features are categorical? As the documentation says here, these values classify the samples into sets of similar samples. So within categorical features are the values nominal, ordinal, ratio, or interval-based. And so that affects how if you wanted to display the data in some fashion, that's obviously something you would need to know. So like passenger class, that makes sense that it would be ordinal, first class, second class, third class. Categorical is survived. I mean, I would say it's better to survive than not to survive, but it's not that's not something you can actually quantify. And so those would be just considered categorical. And then sex, again, male or female, that's something you could represent, with like 0 and 1 and that sort of thing. So there are some mixed data types. I'm not going to get into those because that's not super relevant. Now here's something that is super relevant. Which features may contain errors or typos? This is why a lot of people who work with a lot of data don't like things like full names, especially when it's last name, comma, first name. There's like, the more stuff you get in one column, the more potential there is for error. Like, I don't know if any of you have dealt with, say, a mailing list, and you see like a whole address in there. It's like, oh man, I'm never going to be able to sort this by zip code now. Or you have to write a little script to actually parse out the address into street address, city, state, and zip code, that sort of thing. So these are you actually spend a surprising chunk of your time parsing out the data in ways like that. So another thing you have to consider is we don't have all of this information available for all the passengers, and so we have to decide how we're going to handle, if a particular field is empty. Do we want to assign it a default value? Do we want to have a special marker value for null? That is going to depend on the application. So this is one of those things talked about. Cabin, we don't have cabin data for everybody. We don't have age for everybody, that sort of thing. So you can get descriptive statistics once you've loaded everything into your algorithm. This is working with something called pandas, which is a very popular library in Python for handling data frames and that sort of thing. That makes it so we have 891 instances of we have 891 non-null values, and it's got the data type and all that. And so age, we have much fewer. And then that's a floating point. And then for cabin, we don't have much data at all for that. So, and then we can have our usual descriptive statistics for things that are applicable. So like for the passenger ID, this is the total count, and the standard deviation, that's not For passenger ID, that's not super useful, but it does calculate them for things like age and the number of people traveling with them, the fare. That actually might be more useful information. And you can learn how the data is distributed, how a feature is distributed across your data set and things like that. So what we want to do is find out which features correlate strongly with survival one way or the other. And so that's just a simple statistical calculation that we can do. But as we'll see as we analyze more data, there isn't just one feature that predicts by itself whether a passenger was likely to survive or not. We also might want to create a new feature, basically a calculated feature based on two of the previous features. Like, do we really need to put parents and children separately from siblings and spouses? Probably not. Like, we could combine all that into just family size, and that's probably more useful than either of those two by itself. So again, these are the sorts of decisions you have to make. The data doesn't come ready-made for you to just press the button and get cool answers. And so we know some things that women were more likely to have survived. Women were steered towards the lifeboats first, as were children, and upper class passengers were more likely to have survived for a variety of reasons. And so we can we compute correlation, and we can see that just based on passenger class, first class, you probably can't see that, can you? But it shows that passenger class, people traveling in first class, a little less than 63% of those people survived, whereas in third class, only 24% of those passengers survived. So already just, our model isn't perfect yet, but already we know something significant. Okay, whereas the second class is, as you would expect, somewhere in the middle, it's at around 47%. So we already have something that, it's not everything, but at least tells us something useful about the passenger list. We can look at sex or gender, however you want to call it, and female passengers were regardless of class, were significantly more likely to survive than male passengers. About 74% of female passengers survived, whereas only 19% of male passengers survived. So, and then and it turns out there actually is a bit of a correlation between family size and whether a passenger survived or not. People with larger families survived less. So, and maybe because people, the more third class passengers were likely to have larger families and that sort of thing. Python libraries for visualizing your data, so that's super handy. The one we're going to see here is called Seaborn, and you can actually get, they don't do it here, but you can actually get really fancy with it and tell it what kind of colors you want to use and all kinds of stuff. And so this just plots age versus survival. So here are the passengers who didn't survive on the left and the age distribution of those passengers. And here on the right is the age distribution of the passengers who did survive. And you notice the very old and the very young were more likely to survive, whereas the 20 to 35-ish, the odds were not so good, especially if you were male. So these are the kinds of things you can do interactively in a Jupyter notebook, and you can actually go back and you can change this as you go and plot different things. And it's a lot of fun. So here are some more grids. This is comparing passenger class and those who survived, and those who survived or didn't. And so this is adding more features. So this is this is class and survival, but also with a, or sorry, it is age and survival, but also with a class breakdown. So this is all the first class passengers. Yeah, notice more of them survived who didn't, whereas with third class, it's the opposite. So, and then it's got an age breakdown for each of those. I'll put a link to this on the meetup page so you can browse this at your leisure. You can actually, what I tried to do is I tried to fork the notebook so I could run through this interactively, but once you do this on your home network, presumably you'll have more success than I did here. But you'll get to see stuff like this, which is kind of, this, we're getting closer to useful information, right? So we know that age is somewhat of a predictor. Class is definitely a predictor. And then, just as a slight interlude, we looked at the port where the passengers embarked, and it turns out that's actually not super useful. So, and we don't have that information on a lot of our passengers anyway. But it's nice to know. It's nice to see some of the other ways that you can use Seaborn to plot different things. So we see some more stuff with embarked this port, the other port. It's we don't see the same imbalance as we do here with the age and class information. So wrangling the data, that's what all this stuff is, computing calculated features or eliminating features, that sort of thing. That's all part of data wrangling. So that's the actual execution of the algorithms is totally the easy part. So the data wrangling is where you will spend a lot of your time and effort. So, and the reason you want to drop features whenever possible is because these things are very processor intensive and can, especially with some algorithms, can take a really, really long time. And so if you see a feature, yes?
I was just curious, I've seen random data and clean data.
Yes, yeah, cleaning data, yeah, same thing. So, yeah, cleaning data tends to, I would say cleaning data is a subset of wrangling data, because cleaning data is things like making sure you have everything in the proper format and things like that. Wrangling data is like getting disparate databases together and and making choices about what features you want to use and that sort of thing. But cleaning data is an important part of wrangling data. Thank you for pointing that out. So, but you might want to drop features sometimes, because if you see, like we saw with, port doesn't seem to have a lot of effect on whether a passenger survived or not. So we can leave that out and save some time and processing power, because some of these algorithms can run for days if left unchecked, depending on how you want to do them. And so if you can reduce the size of your input, that is always a good thing. So we've got, so this is talk about some ideas. So is this the one that, and then presumably name and passenger ID are some more some more features that don't, presumably if your name was Smith versus whether your name was Jones, that probably doesn't matter to your survival nearly as much as other features. However, there is something to note about when they have title, like Mr. or Ms. or whatever, you do find some kind of unexpected correlation, because this is kind of a function of the time in the class, but it used to be common to call little boys master until they reached like their teens or so. Like if you're like, I don't know, are there any little boys in Downton Abbey? I don't think there are. But like think that era, think Merchant Ivory is like, Master William, but that's how they used to refer to little boys. And so if somebody's called master, that means they're, so like it says here, master title has a mean age of 5 years. And so, and then somebody with the title lady or madame is, reasonably assumed to be an adult woman. So there is a bit of correlation there, but you probably, don't need to read too much into that. Like the classic statistics thing you might have heard about the correlation between wearing skirts and breast cancer. I mean, that's true, but it's not very useful information, right? So that's kind of, this is a classic example. Correlation does not imply causation. So, but for now, they're going to go ahead and keep the title feature. You can always take it out later. So, and then they have ways they're handling, and then this is another thing you'll end up doing a lot. You'll see things expressed slightly differently. So something that was miss, that was generally used to refer to young unmarried women back in the day, or mademoiselle if you are French. Those are more or less the same title, but if you didn't tell your model to treat those the same, it would treat them differently. So that's something to be aware of. So this is more title stuff. Not gonna, and then it just infers the title from, it classifies things as it should. So I think that's okay. Let's see how we're doing on. Let me see how we're doing on time. Oh goodness. Okay, so we've got some more grids, and okay, so this is looking at class versus gender. It's 0 for male and 1 for female, and as we have talked about earlier, if you were male and third class, especially if you were between about like 18 and 35, chances are you did not get to tell your story. So, just like in the film. So. And so we mentioned earlier that we didn't have age data for all of our passengers. And so it probably doesn't make sense to assume a default age for everybody. And so the way this notebook goes about it is based on class and gender, it tries to approximate a person's age, which I actually thought was really clever. So another thing it tries, and this is another thing you'll do a lot with continuous data, is something called banding. So technically with age, all of these, so like 22, 38, 26, 35, and so on, are each distinct values, but you can generally kind of break those up into buckets. And so you only have, so instead of dealing with 891 different potential age values, you're dealing with, say, 10. Say, okay, so we want, 0 to 5, 6 to 10, 11 to 15, and so on and so on. And that can be, and how you decide to pick your buckets, that's a whole nother conversation, but that's another example of the kinds of decisions you'll be making. And so by making age bands here, we start with 0 to 16, and they showed a survival rate of 55%, and this is independent of all other factors, whereas 16 to 32 showed the lowest survival rate at a little less than 34%, and then the rates got generally higher, although there is some outliers here for some of the very oldest passengers. So. And so you can replace the continuous data of age with the age band information, and that makes it easier for the algorithm to do its thing. And so here I talked about the possibility of doing this earlier, basically creating a family size feature out of siblings and spouse, basically adding siblings and spouses to parents and children, +1 to count the passenger themselves, and then that's their total family size. And as we see here, family size actually, for the most part, tends to drop off as it gets larger. Passengers with larger families survived a lot less than those. If you had a family size of 3 or 4, then you were 2, 3, or 4 was good. But after that, it was anything outside of that, the odds started to get rough really quickly. So then even something as simple as, you can create a feature, so if a passenger is traveling by themselves, and, well, how do we determine that? Well, if they have a family size of 1, then they're alone, right? And that's exactly what the code does here. And it turns out you can learn a little bit even from that. People traveling alone were less likely to survive than people who weren't. So let's see. Talk about, okay, this is more about port stuff. That's not super interesting. We can, okay, it talks about the way it has ports listed is by a single letter. I don't remember what they stand for. It's not super relevant, but when given the choice in machine learning, you almost always want to represent your data with numbers. And if you can represent that data with integers, even better. Computers love, okay, so first of all, does anybody not know what I mean when I talk about integers versus floating point numbers? I should probably, okay, good. Computers love integers because they're fixed within memory and they're easy to process. Floating point numbers are complicated and cost more processing power. If you've ever taken computer organization or computer architecture, you know what I'm talking about. So we've got another example of continuous data was the fare paid, the price paid for the ticket. And similarly as with age, we can band those. So instead of, again, dealing with a potential 891 values, they've broken it down into 4 bands, which, again, makes things a lot simpler. And we see, surprise, surprise, the more you paid for your ticket, the likelier you were to survive. Who'd have thunk? So. And so this next bit of code is just converting the actual fare value to the corresponding fare band and that sort of thing. And then all of a sudden, we see something that is much harder for humans to read, but a lot easier for computers to read. And so this is why it's important to document your process, because if someone just handed you this, you would be like, I don't know what this is. So it's important to keep track of all the steps you do to create new features and band features and that sort of thing. Now we're actually getting to the fun stuff. This is where we feed it into the algorithm and cool stuff comes out. But this is why the demand for data scientists has not kept up with supply, because the supply has to get through all this less glamorous stuff to get to the fun stuff. So you have a variety of algorithms that you can choose to model your problem. And which one is appropriate is going to depend on several things: what problem you're trying to solve, how much time and computational resources you have, how much accuracy you need, depending on, if you're, say, trying to create a model for a medical diagnostic test, like, you're going to need 99 point, a few nines back there. If you're just trying to do market segmentation, you probably don't need that level of accuracy. And so these are the kinds of questions you have to ask yourself. So, so this talks about using a method called logistic regression, and it measures the relation. It just measures the relationship between the feature you're trying to predict, whether a passenger survived or not, compared to the feature vector, all the other data that we saw. And with our with this method, they're able to predict survival rates with 80.3599999 so on percent accuracy. Not bad, but we can probably do better. So let's look, and then they talk some more about what logistic regression does and some ways you can tweak it a little bit, and talks about here at the end, it points out the correlation between how strong the correlation between a particular feature is and survival. So sex is pretty high. As you know, we've seen with some of the previous breakdowns, female passengers were a lot more likely to survive. And then on the other end, passenger class is another. It actually has a strong negative correlation because, you know, as your passenger class number gets higher, you know, as at 1, 2, 3, your chances of survival get lower. So that's why that's a negative number there. So another example is support vector machines. That's another algorithm. I'm not going to get into the details of what each algorithm does, but it's another way of approaching. It's another way of approaching the problem. It's a little bit more computationally expensive, but we also get more accuracy. This gets us up to almost 84%. It's 83.84%. And then this is just at the end. This is comparing the accuracy of different kinds of methods. So this is using k nearest neighbors, which is kind of interesting. And then naive Bayes, perceptron. This was one of the first features. It was the perceptron was something created in the 60s to try and emulate a single human neuron, and then based on the inputs, and a given threshold, the perceptron would decide whether to fire or not. And then that was what gave rise to what you hear a lot about neural networks today. Yes. Let's see. I don't think we've got to any neural networks yet. This is presumably just whatever sklearn's default is for perceptrons. So there's a perceptron class in sklearn is scikit-learn, by the way. I'll talk more about that in a little bit. And then do we have anything? And then decision trees. This one I actually will talk about a little bit because it's one of the easiest to explain to people who aren't familiar with machine learning. And it's say, given a your set of data and a set of features, how can we split them in a way that's meaningful? So like say the first question you would try this by building different kinds of trees and see which one gave you the best results. But so say first you split by gender, okay, and so if the passenger is female, go to this branch of the tree. If the passenger is male, go to this branch of the tree, and then from there it's like, okay, well, what class are they? And usually in relatively few steps you can build something pretty useful with a decision tree. Random forest basically takes this principle and amps it up to the nth degree. You know how I was talking earlier about how the main advantage of a machine is it can crunch numbers way faster than you? Well, it applies that same principle to building decision trees. Random forest just randomly builds a bunch of decision trees based on the features and the data you have, and then automatically selects the best performing ones. Obviously it takes a hot second to do this, so you wouldn't want to bust it out for simple problems, but for things that, and notice that this gets us a pretty high accuracy rate, 86.76. That's, we've improved almost 7 points from our initial classifier. And so we've actually got our algorithm performances here at the bottom. Random forest and decision tree performed at the top. With a small data set, you would expect these to be pretty close, as they are here. And then it goes on down the line with something called naive Bayes, which is just an application of conditional probability. If you took statistics, you might remember Bayes' theorem and all that kind of stuff. So, okay. So that is the demo. And let's see, I'm gonna switch back to my slides. And the live streamers are gonna see my face again for a few seconds. Hi, everyone. Hope you're still awake. Application window. We're going to pick back up with the last few slides. Okay, so if you've found this stuff really interesting and want to learn some more, I will point you in the direction of some resources. The first one is some programming and related tools. The notebook we just looked at was in Python, as I mentioned. So if there are other languages, but I would recommend starting with Python. Scikit-learn is one of the most common libraries available. When you get really fancy, if you want to get into neural networks and stuff, there's a library called TensorFlow. And that's, I mentioned the perceptrons. A neural network tries to aggregate a bunch of those, and they're one of the most accurate, but also one of the most computationally expensive approaches to machine learning. So I don't recommend starting out with something like that, but when you're ready for it, know that it's out there. R is, sorry? Let's see. I think it depends on where you're doing your data science. I think industry tends to favor Python a little bit, because Python you can also plug into like web libraries and stuff like that. But there's a heavy R community out there. In fact, I'm working my way through an online course right now about R that's targeted for journalists, because a lot more news stories are dealing with data, and R is actually pretty easy to set up and get started with. So I would say Python's probably a bit more popular, but like I don't think you would struggle to get a job if you chose to focus on R instead. So, and honestly, and I say this as someone who has taught beginning programming before, the hardest language to pick up is your first. Whatever your first programming language is, that's the hardest one to pick up. Once you've picked up one, it's not super difficult to pick up the other. So there's a good chance you'll be using bits of both. So. And RapidMiner is not a programming tool per se, but it's fun for like quick and dirty prototyping, like Ruby on Rails has been for web development. If you want something up and running quick, in fact, you can download a sample tutorial for RapidMiner where you just like drag and drop things with the data and you try and run different models on it, much like we did with the Python notebook. And so that's kind of fun. And they have a free community edition. So some educational resources. So some websites, Kaggle, which was the one where we saw the notebook. They also have competitions, and some of these competitions have like meaningful prizes, like thousands of dollars. Like companies will put out challenges and say, okay, give us your solutions, and the top so many will get cash money as prizes. So that's pretty cool. And KD Nuggets is another good one. They also have a newsletter. It's a good just like clearinghouse for like what's going on in the trenches of machine learning and data science right now. And then podcasts. I love a podcast. So I don't know if y'all love podcasts, but y'all are going to hear some recommendations. Data Skeptic is a good one. They're doing a really interesting series right now on fake news detection. And that's something that's something that humans are struggling with, and so machines are struggling with it as well. But it's something we can at least look at. And linear digressions is another fun one. And so a little more about TechMill. I know some of you are already familiar, but some of you might not be. It's a local 501c3 nonprofit dedicated to growing and supporting the tech community in Denton through events like this one. We also have social events, and I've seen some of you at some of those. Like last night we had our APIs and IPAs, which we have every 2 weeks, where we just get together and shoot the breeze over some beer or whatever you like to drink. Our meetup page generally has our most current event calendar. I think that's how most of you found this one. So that's where all the current information about upcoming events is going to be. We're TechMill Denton on most social media. We have a Slack channel. I know some of you are in it already, but for those of you who aren't, just go to slack.techmill.co. Make sure you go .co and not .com. It might take a few seconds to come up, but a button will come up eventually, and you can press it and enter your email address, and you will be invited to our Slack channel, and you can talk with us, cool people about tech or anything else that is on your mind, as long as you do it in the right room. So, and if you want to follow me on Twitter, I am at Algorithm Blues. So, because I love a pun. So, some acknowledgments. I want to thank Heather Gregory for letting us use this space. Stoke has been very kind to us at TechMill. Kyle Taylor, who is out of town for the next few days, but he came up with the idea for the summer series, and he presented the last 2 sessions on Google Analytics. And you, most importantly, thank you for coming and sharing this, taking some time out of your evening where you could be, binge watching The Handmaid's Tale or something. So I thank you for taking time out of your schedule and joining us. So any questions? Does anybody have any questions that they didn't get, or comments, suggestions? Yes. Sure. Mm-hmm. Yes. Yeah. Yeah. Yeah, they provided the data.
How do you go about deciding which data to put into? With some of the data you have.
Right.
Which cabinet? It's only going to be presidency or whatever.
Right.
On there versus the lower text where hundreds of people.
Right.
You just like split the husband and wife in one, put the other in treatments that for just. Because I imagine for treatments that.
Okay, yeah, I know what you're talking about. Right, and so for those of you who are following on the live stream, you probably can't hear the question, but he asked about how you choose your training set and your test set, and is it necessary to have representations of all kinds of, or all possible values of features in your training set. And actually, most of the time, it's not. The exception to that is when you have a highly unbalanced training set, when you have a highly unbalanced data set. So like spam. Like, as much of a pain as it is, it's a very small percentage of the actual email we receive. So for things like that, it is important to make sure you have some decent spam examples in your training set. But for stuff like this where there's multiple features in play, it's usually not as necessary as you might think. Does that answer your question? Did I see another hand up? Or? Okay, well, in that case, I will go ahead and stop the broadcast for those of you on YouTube. Thanks for coming and watching live. This is just for the YouTubers. And this will be up for posterity, and hope you enjoy it.